back. Welcome to another exciting computer architecture lecture. I hope you guys all made it out okay from the snow. We had 38 inches of snow in Milford. But because I have competitive colleagues, they point out, well, that in Woodbridge they had 40 inches of snow. Well, it isn't a contest. But if it was a contest, I lose. Too bad for me. So what I thought I would do today is start the class by reviewing some of your homework efforts. And so using the magic of Axiom Mentor, I have downloaded all of the homeworks onto the hard drive, and I thought I would review your little linear regulators. So just to recap, for those who are watching without having seen the prior episode of this exciting series, in our last exciting episode, we were designing LM305 regulators so that we could get 5 volts. Because 5 volts is a good voltage to have for computers. Computers like 5 volts. They also like 3 volts, but 5 volts is also good. It turns out if you're doing Arduinos, what you'll find is that on every Arduino board, Uno, Duo Milanove, even Leonardo, and certainly the 2650 Mega, I think that covers the common variants of Arduino, you will find that there is this teeny weeny little regulator. And it looks just like a great big normal regulator, only there's a difference. And the difference is it can only handle about 1/4 of an amp. And as a result, it has no heat sink. It also means that when you overvoltage these things, it blows up immediately, I'm here to tell you, from experience. So that means you can't run it at 12 volts. Don't plug it into your car and expect it to regulate it down to 5 volts because it overheats right away. And then you have a blown out board. Well, you have a blown out regulator on a board, which is very hard to replace, by the way. But you can still make it work if you just plug it into the USB, sort of. But it becomes somewhat unreliable. Bottom line, you want 9 volts as a nominal input voltage for a 5 volt regulator, which means you can run it off a 9 volt battery as long as you're not drawing substantial power. Little transistor batteries will work. Let's see if we can find some of the oh, here it is. Homework. So, who shall we start with first? I guess this is Kyle. Let's see, what do we got here? So here's my little linear regulator. I like the LED. That's a nice touch, because that shows we've got the 5 volts coming in, and it's working. And we've got a current limiting resistor here. What value is that? You see, you need a value, because otherwise you can't get a... Well, I think if you ever want to make something, you're going to need to know what value. That's a design parameter. Engineers can spec it. And let me give you an example. If you assume that the forward voltage drop on a diode is 0.7 of a volt, then what you can do is you can compute the power that it obtains based on the resistance you put in online, or in line with it. And so if you know that it's a 20 milliamp device, because that's what the device wants, then what you want to do is you want to take 20 over 1,000, multiply it by the 0.7 of a volt drop. I'll just do it here in the text field. You probably have seen this before, but E equals IR, right? So you start off with E equals a 0.7 volt drop. And then what you want to do is you want to say I, and you want to make that milliamps into amps, right? So think of it this way. 20 milliamps, okay, so 20 over, like, I don't know, 1,000, times R. Now solve for R. Right? So now I have something like 700 over 20, which is probably 70 over 2, which is like 35. Is that right? Something like that. I don't know. I'll let you guys sort of grok that one. So R equals 1,000 times 0.7 divided by 20, which equals 700. Is that right? Or 70? 70 over 20, which equals 35. Does that sound about right? 70 over, I'm sorry, 7 over 2 is 3.5. So that doesn't seem right to me. Maybe what you want to do is compute the voltage drop not at 7/10 of a volt, but at 7/10 of a volt minus 5 volts, because that's what the whole drop will be. 7/10 of a volt will be the forward voltage over the diode, because it doesn't, I mean, we're not even in the ballpark. 5 minus 7/10 of a volt, that's 4.3 volts. 4.3 volts over 20 is probably closer. So probably get a notepad and do this nicely. Notepad. I just want to do this so that it's not so crappy. Excuse me while I become less crappy. Select all, cut. I want to do a voltage. I'm expecting this part is correct. The voltage drop will probably be 5 volts total. But I expect 7/10 of a volt from the diode. So the total voltage drop will be 5 volts minus the voltage drop off the diode, which ought to be something like 4.3 volts. And that ought to equal the current load required for the LED. So I'm putting that at 20 milliamps times R. And now I want to solve for R. Does that sort of look about right? So now I say R equals 4.3. Let's see if I got that right. Times 1,000 over 20. Does that sound about right? So now I got 4,300 divided by 20, which equals 430 over 2, which equals 220 ohms. Oh yeah? Yeah, ohms. Okay, so then what I would do in a case like that is I would look up common resistances, and if I found that 215 or 211 or some odd number of ohms like that wasn't common, I would round it up. So if somebody said you can get 220 ohm resistors because they're common, I would just say, okay, 220 ohms, good enough for me. And that would be my current limiting resistor. So then what I would do is sanity check. I might Google it or something and say common current limiting resistor for an LED. And you know, everybody asks, why do I need a resistor? And of course the answer is because you have to limit the current it draws. And here's somebody who did the same computation. And what did they come up with? 23 ohms? Oh, but they've got different voltages because they're running this at a smaller voltage. But they can give you a nice example. Let's see, what current did they want? Oh, it doesn't look like this is a practical circuit. what is this LED calc thing? I've never seen this. Enter the voltage, 5 volts. Voltage drop across the LED, 0.7. Desired LED current, 20. How many LEDs to connect? 1. Click to calculate. And there it is. Nearest higher rated resistor, 220 ohms. You need 1/8 of a watt. Exact calculation, 215. I mean, somebody took Ohm's law and turned it into JavaScript and made it graphical. But this is kind of cool, because if you said to me, well, I want 10 LEDs, and I know they're each going to take some current and provide me with some voltage drop, then I have to divide it up because I can't do it all. So maybe if I crank it down to, let's say, 5 LEDs, at some point I can just keep adding LEDs and reducing resistances. 8. Yeah. So at 7, why is that? Let's see. 7 times 7/10 of a volt per LED drop is going to be 4.9 volts. Right? So basically, what that says is if you have enough LEDs, you'll have enough voltage drop with enough current required so that your resistor has become very small. Here it says 5.6 ohms. I mean, that's a very tiny resistor. So I know, you're not supposed to do that. I think it still takes a message, right? No? Who knows? It's not a smartphone. It just makes phone calls. That's all it does, really. So, ideally, if you said, geez, I just want a light bar for my, let's say, here's a good application. You'll like this. I want cool lights for my car, right? Cars run on 12 volts, but sometimes they run as high as 14 volts. So now if I click to calculate, it says I got enough for I don't know, 25 of these things. Maybe less. 20. Yeah, I'm close. 19. There you go. So if I had, let's say, 20 of these things all in a row, I could probably get them all to light up without any resistor at all. They would just be a little less bright because they wouldn't be getting the full 20 milliamps. So if I ran it at 20 of these things, click to calculate, and then ran them a little bit dimmer, 19 milliamps. Yeah, he's not doing it for me. I have a feeling I could get all 20 of them to light up. Of course, I might just blow them out, but I got to get them all lined up in a row. And you know, the LEDs last like 10 years, maybe more. And so, and that's continuous operation. And I don't run the car for 10 years continuous. So as a result, I expect them to last the life of the car. Maybe longer. So you can make nice LED... What did they call it? You could pimp your ride. Right? You don't watch that show? Oh, it's a little old, I know, but if you wanted to, you could pimp your ride. Actually, what you've really done is you've geeked your ride. It's just much better. Especially if they're blinky LEDs. Then you don't have to turn them all on at once. That's a good application. So, back to the schematic. I'm thinking 220 ohms is a good value here. And it's nice because it displays it. Here's a diode. Let's see what the properties are. And you know, you're going to need a value of some sort, I suppose, if you're going to sit there and, you know, cost out your board and actually build something. So at some point, you'll need to do the computation and figure out, you know, how much current the diode needs. Probably you want something that can stand a forward voltage of an amp. I'm thinking there's a diode. I'm just going off the top of my head. I'm not real familiar with what's out there, but the 1004 diode, what does that do for me? You know, after a fashion, you become real familiar with parts and their specs. But if you're not, you Google it, and people will tell you, just like I did here with the LED for the current limiting resistor. So important, right? Little things like that make it work. Because you know what's going to happen when you assemble it and you get it wrong is you'll just blow out the LED and you'll go, what's wrong? You get binary information. It either blew out or it didn't blow out, and it either worked or it didn't work, and you'll be like, oh crap, what did I do wrong now? Well, my little data search didn't help me much. Where can I get the diode? Data sheets. Here's a data sheet. Here's a diode on eBay. That's silly. Well, here it says it's a 1 amp rectifier. It'll go up to 400 volts. So maybe that's a little on the high side. You do want to be able to handle an amp. So maybe the diode you want could be 1001, I suppose, or something like that. But there it is. These are common. Now, probably you could get this in a surface mount configuration so you don't have to drill the holes, and so you can use an automated pick and place machine. But if you're old school like me, you're soldering these boards by hand at home just to try and get a prototype out the door. That's typical. That's what I do. You know, I can turn a board around with parts in an hour. Printed circuit board, etching and everything. So that's really nice, because otherwise what happens is I have to wait a real long time. And if you think that you're going to get this board right the first time without making any changes, think again. Right? The goal, it's almost like doing a word processor. You want revision, and you will converge to a correct board, but it will take you more than one try. It always does. And if you have to wait 6 weeks for a board to come back from China, that's a bummer, because now you've put 6 weeks into the life cycle of your product. So I'm totally into quick turnaround time on boards. In order to achieve that here in-house, we have two mechanisms in place. One uses what I call subtractive synthesis. It's an LPF router. It's very nice. It's like a $10,000 PC board milling machine in the basement, and we can use it. And it will take the Gerber files straight out of the Eagle, so you can drive it. They call them G-code files. PCB. I wish I could show you a picture. Images? Do they show pictures on there? They show the router images. I want to see the actual machine. They don't show me the machine. I got it downstairs. Well, that's too bad. PCB router. Images. There it is. That's it. We got that. And so what this does is it gives you a gantry that moves in and out, and it has a little stepper motor that'll come down, and then it has a high-speed milling machine which mills out small copper traces from the copper board. No chemicals. And it's driven by a dedicated PC, and the PC interfaces to this thing through a little USB port. So it's a peripheral. In fact, it's like a printer. It's just like a printer, only with a difference. It's kind of like a pen plotter, where pen up is drill head up, and pen down is drill head down, and the X and Y commands are pretty much the same. If you've ever seen a pen plotter work, it's real fascinating to watch. The pens go and then it changes pens. This thing can change bits. And it will also drill through if you need to do through hole. And it was also very careful to be aligned. So if you've got your alignment hole set, you can flip the board over. It'll do the other side too. But then I hear you say, how do you do the through hole plating? The through-hole plating, that's when you have a hole, but there's no conductor on the edges of the hole. So what we have is rivets. Rivets. And you take the rivets, they're little tiny rivets, the number 60-bit sized rivets, and you mount them into the auger of a drill press, and you can press the rivets home, and they flare out, and that gives you the plate through for the board if you want to do a two-sided board. Painful. You're much better off changing your design to make it one-sided. There's another way, my favorite way. I don't have this at home. Right? I find a $10,000 machine offends my now famous sense of thrift. So what I do at home is I use ammonium persulfate, which is a copper etchant, and I use a resist which comes from the toner of my laser printer. And what I do is I print onto shiny paper. You can actually print onto magazine paper. Then I run the shiny paper on top of the printed circuit board through an iron-on transfer machine, a little laminate machine which you can pick up for cheap in a thrift store or even an office supply shop if you want to, and that transfers the toner directly onto the board. Then I just pop the board into the etchant and it goes bzzz, and it takes an hour, and then bam, you're done. If you heat up the etchant and bubble a little bit, and I have an etchant tank here for us to use if we want to, it runs a little bit faster, actually quite a bit faster. Once the etchant gets depleted, it runs slower and slower still. And the PNP, it's called Press in Peel Toner Transfer. I've done several boards this way, and I've got the blue film for it. This is the professional build film instead of like the shiny magazine paper. And toner, I don't know if you know, toner from a laser printer is really submicron plastic. It's powder, and it's very dangerous. I don't know if you knew this, but if you're recharging toner cartridges and you get the dust in your lungs, you can't expectorate it. It sticks in your lungs and you can't cough it out. So, it's one of those I'm not careful enough with it, but I should be kind of things. You don't want it in your eyes, you don't want it in your lungs. It's nasty stuff. And this is the Press and Peel toner film on eBay. And so this is the product I use. What is he charging? 100 sheets for... Oh, there's like $1 a sheet. Anyways, I don't use a whole sheet for small boards, and I only do small boards if I'm doing single-sided boards. And I've done computers this way. Not like desktop computers, but microcontrollers. So this is good. This is looking fine. It's got a nice switch. Do we know anything about this switch? Oh. That looks nice. So can I, is there a board for this? Should be, right? Okay, so you did the schematic and that's fine. No board. You got the board? Alright. So we won't save that. I thought the little lesson on the Ohm's Law was pretty okay. Was people alright with that? You've seen Ohm's Law, but this is more like a practical application, so that makes it kind of nice, because it makes you feel like you didn't waste your time in Physics 1 or something. I don't know if people in Physics 1 actually tell you how to compute a current limiting resistor or not, but when I took physics, I went to my physics teacher and I said, "Oh, Professor so-and-so, could you please tell me how to do the computation for the value of a bypass capacitor for my static RAM card?" I don't know how to do that. It's like, oh gee. Then I went back later and I asked, high-end college level, this was like in high school, I asked high-end college level physicists, I said, "Oh, I'm taking a ceramics class and I'm building a ceramic flute. Can you tell me how to compute where to put the holes?" I don't know how to do that. So it's like, okay, what good is this physics for anyway? You can't, I mean, the holes of a tube in a flute, that sounds like the most elementary thing. In fact, there is a good way to do this with physics, but is this yours? Okay. This one, jeez. Oh, wait, where are we here? I was going in order. But that's not in order. I started here. I was going to go to Jason. Okay. Let's do this. Open with zip. So this is Tarek. Oh, that looks good. Did you get yourself, no. Okay, we'll put that in there. Apply. Okay. Did you get yourself a diode in here? What else? I guess that's it. You got everything else. Now if I switch over to the board, there you go. That's great. So this looks like an electrolytic, oh no, that's a cap, that's a switch. This is, now that thing, forgive me if I, wouldn't it have been better to rotate this a little bit? Oh, I guess I went the wrong way. Is there a way to go the other way when you rotate? There you go. Now there should be like a way to move it, right? There we are. Sometimes there's a, I don't know, perhaps I could call it conservation of a board space, but if you lay out your board nicely, you can probably, can I move this? It should move. Yeah, there we go. You can probably make the board a little smaller, and I don't know if I mentioned this to you or not, but smaller boards are cheaper. I'm not sure why the outline here is, this is like in the silkscreen layer, right? For some reason that's not, yeah, there is a rat's nest thing in here. This one? There it is. Do I have to click to rat's nest it? Maybe I've selected the wrong layer. No, but I like the fact that this is done. No, I just wanted to sort of get you guys doing the schematic. The LM, well, the 7805 regulator was done by this class last time, and we made boards. It wasn't a particularly fancy thing. I could show you the boards that came back, but I just thought it was interesting that people had actually gone through the process. We used batch PCB. When the boards came back, it was after the final, and as a result, the students didn't get a chance to see their work, which is, I thought, really too bad. When you go to make these boards, making them as small as you can, make them as compact as you can, and it's just going to save us money. Projects. I'm going to do projects like this, if that's alright. Now this error, FB annotation has been severed. This seems to happen a lot when you start moving files into different file systems. It seems like zipping it up and moving it over causes this error to occur. And I think there's a way to fix it, but I don't know how yet. I just started Googling this error earlier today to try and see why this is occurring. So that seems to work. Let's look at some others. I've got something here from Stephanie. Looks like she opened it. Oh, I think she's uploaded 3 times. I'm going to go with the 3rd try. Well, that doesn't look right. It hasn't been placed yet. Let's try it again. I don't know what that was. Let's try it again. Oh, there you go. So apparently when you upload it, you can't delete it. Once you upload a file, it's immortal. So if you're trying it and uploading it and it doesn't work out for you and you do it again, then it comes out so that I see multiple versions. There should be a way to open an RAR file. Anybody know how to do that? Does this WinZip open RAR? I guess so. So that's going to be Pablo. Let's see how he did here. I've got a schematic. Oh, and that looks fine. Everybody seems to have the same schematic here. All right, that's good. That's fine. Actually, that's fine. That's just what I was thinking. Now I've got the spinning beach ball of death, which is always good. That's like a Windows thing, right? Task manager. I can't even get the task manager. Do people actually like Windows? What have I done here? Did I just lose my whole session? Oh, is this one of those you have to be patient things? Oh. I mean, it's not like anyone else is watching. Oh, wait, they are. Let's just close a few things. Maybe that will fix it. Of course, the end of that sentence is, I hope. Now, where did my stuff go? I mean, I just downloaded a bunch of stuff, right? This? Okay. How do I show this in folder? Oh, there we go. So somewhere in here, thank you, I'm back. Wow, that was easy. Not. So we got Stephanie, Pablo, he opened, and I think we didn't get quite there yet. Or did we? Oh no, we did. We opened it. Okay, so then comes Albert. Open with Zip File Manager. Hope you don't find this tedious, but I like to see what others are doing, and I'm sure you do too. So let's see what we got. Looks good. And there's a board layout. And that looks like a... let's switch back. He got the right package, but he didn't tell us about the value. So to make it right, you probably want to throw a value in there. You know, you're not going to be able to get a price quote on your device for manufacture if you don't throw in a value. I just changed the diode like every time I did this. I think 1001 is fine because it goes to 100 volts. And 100 volts sounds like plenty. So that's 1 amp at 100 volts. Let's flip it. And I can see the value of the resistor. Where is the diode? Oh, there it is. So then someone once said to me, geez, how come you're using all this whole plate-through stuff in your new Kickstarter board? Wouldn't it be cheaper if you just used surface mount? And I said, well, we have a jack, and by doing a hole for the jack, I can make sure I have a good mechanical mount. And I thought that was very important because people will plug things into the jack and it'll create a great deal of torque on the surface of the board. So a through hole made sense to me. I've got, you know, a turn pot, and the turn pot is one of those things you lay your hands on and actually turn. And it's got a knob, so that's got a lot of torque on it too. So mechanical considerations are quite important when you do these things. If you've got an IC like this, the LM305, the 7805, then you're going to have an issue with a heatsink. You've got to have room for your heatsink. And you're going to have room for ventilating that heatsink unless you're planning on putting on something like a fan. You need room for circulation. So heat is another issue. Heat will build up in an enclosure. You may not find that, it's not a lot of heat, it's only a watt. Well, guess what? 1 watt inside of a totally tight plastic case is going to burn up all your components and you'll have very limited life. So you'll have to start thinking in terms of putting holes in that case, something to vent it, or else the heat will build up. If you're using a metal case, you might like to just take the a screw and run it through the hole here in your metal case and use a little heatsink compound and get the case to act as your heatsink. That's great. That'll work. Because that heatsink, if it's metal, yeah, that's what Apple does. If you have a Apple laptop, an old one like I have, it's like an 800 megahertz PowerBook, it runs hot. But if you get some ice packs and you just throw it on top of the ice packs, what happens is the fan inside turns off because the thing's all cool and happy, and you can make it run quiet. So it's an interesting trade-off. Apple is totally into making systems that just bake. The original Mac Pluses and the Mac SEs ran without fans, and people used to get things called fanny packs, and they just throw them on the back because those Macs burnt themselves to bits. They didn't last. Of course, when you bought them, it was 1985. So if you're expecting it to last till 2013, that's beyond the life expectancy of the machine. But you still want it to work because it's cool. Now, if you had, instead of buying one of those $2,000 Macs, bought $2,000 worth of Apple stock, then you would have had something. Alright, so what are we up to now? We did we do Albert? Yeah, that's the one I just did. So now we're down to Jason. Oh, I got the board. Let's do the other. Okay. Oh, we got a value in here. Let's see if we got a value here. No. 1001. Apply. Okay. And there you got it. Values. It's all good. I do Design Link, but it seems to want to take over the screen. That does a search on the database for all the parts, so you can get a price on the bill of materials. Well, I have an idea that you want the cheap one. Oh. Oh. Well, there's one for 29 cents. And there's one for $10. Which one shall I pick? Oh, I know. Designing. Am I designing or am I shopping? Maybe a little of both. They have some, but not too many, and they're cheap. Here they have more, a lot more, and they're just a little bit more expensive. And Arrow Electronics is a well-known firm. In fact, Arrow Electronics has a retail office here in Connecticut. I can pick the phone up and just talk to those guys, so that's good. Shopping. Shopping. This is cheaper and they have more of them. Oh, I missed the 7-cent one. I could have made it cheaper still. I really like the integrated shopping system. Why is this so expensive? This is a... It says he has a speed sensor? No, wait a minute. It says it's a speed sensor. I don't know, but I know we don't need a speed sensor. there's something wrong here. It's supposed to be a resistor. Yeah, I mean, he put in a 330 ohm resistor and it came out as a speed sensor. This. What's this? Something's wrong, Jason. I don't understand. What? This says 330. It says resistor, properties. What happened here? This thing. I'm not sure what that is. I'd have to Google it. But for some reason it's coming up as a $10 speed sensor when it's supposed to be a 2-cent resistor. So that's not right. I think that, you know, that kind of a thing will kill your project, because nobody wants to spend $10 on a speed sensor when they want to spend... But 31 cents for... I mean, what is this thing that it thinks it's a... is there like an open device? What is this? It's a resistor. That's what it's supposed to be. I got confused by that. Let's just make the value 220. Apply. Okay. Oh, wait. There's something in here about smashed. Resistor American symbol. I think that's fine. I'm close. I'm not sure what the issue is here. But there's something going on when it says it's a speed sensor and we know it's not. What if I just... Can I do just one thing? Technology. What is that? Resistor. It's a resistor. What is his problem here? Schematic. If there was some other reason why we would... Oh, wait a minute. What do we got? Now it's 30 cents. That's still a little expensive, but it's a lot... It's a lot less. Oh no, here the price $73? Availability 16? Something's wrong. Yeah, it's a Honeywell VRS speed sensor that runs at 55 volts. I'm totally bamboozled. This number, this order code, and the number is what's messing me up. That order code's got no business being in there. So something's wrong. This order code should be removed somehow. I'm not sure exactly how you do that. That's a thing that we ought to be able to figure out, right? I think what's happened here is he's placed a component in from the component library and he put in the wrong component. And what I would do here is I would take this component, delete it, and then place it in again from the library. I think that's the only, that's the only explanation I can offer. He just put in the wrong component. Because there's just no way this is a $35 component. And obviously, if I wanted to, do a search and find resistors, I could. So let's not waste too much more time on that. So Jason, you got the wrong component in there. Let Jason fix it. So that's good. I think everybody did a reasonably good job. One of the things I wanted to do was I wanted to take a step back now that you're all schematic capture guys and printed circuit board layout guys with good expertise in this area. I thought I would give you a nice practical real-world computer engineering kind of problem to think about. And the first thing I wanted to do was I wanted to describe for you the basic idea behind mixed signal design. When you go into the world of digital design, everything is a switch. It's ones or zeros. Okay, this is the assumption that you make, and it's a good one for Digital Design 1. But here in the real world, nothing is ones and zeros. Everything is analog. And so what you need to do is you need to digitize. Digitization is a process whereby you sample the signal at discrete time intervals. It's also a process whereby you quantize the signal to a fixed number of values. So you need to do both. Digitization means discrete sampling, and it means quantization to a fixed number of values. And when you do a digital to analog converter, you're taking the digital number and you're converting it back to a signal that has a value which ranges between a minimum and a maximum. So that signal value range is typically defined by voltages which you supply to your digital to analog converter. Similarly, voltage references are used in your analog to digital converters in order to be able to constrain the signal. Let me give you an example. I play guitar. I take the guitar and I run it through a digital voltmeter to measure how much voltage is coming out of the guitar. It's a bass guitar, has very good voltage level. Really powerful electrical signal. 60 millivolts. Now I got an ADD converter. It sits on a microcontroller. The ADD converter runs between two voltages, 0 and 5 volts. If you want full deflection on the ADD converter, you can supply a voltage that runs at 5 volts. How much comes out of a bass guitar? 60 millivolts. How much do I want? 2.5 volts nominal. How do you get 60 millivolts into an ADD converter so you can digitize your guitar and jam out with your Arduino? Well, you've got to have an analog amplifier. This is not digital design anymore, folks. Right? So, real practical issue. Put the amplifier in. Now, what is typical line level? Typical line level for audio. 1 volt peak to peak. So this is a big problem because you have -1 to +1. What does the ADD converter want? 0 to 5 volts. So now what do? Well, you throw it in through a decoupling capacitor. Maybe you put in a little bias DC voltage to get it up to about 2.5 volts, so it can be right in the middle of the range of the ADD converter. So you need a reasonably good amplifier that's going to give you good voltage output. It's not just the line level output that you're going to want to get out. You're probably going to want to pump it a little bit to get a full dynamic range out of your ADD converter. So what I said to myself is, gee, my students have never designed an ADD converter. They've never designed a digital to analog converter. They need a lecture on D to A converters and analog to digital converters just to kind of get a feeling for the different kinds of, I'll call them DACs for digital analog converter and A to D converters available. You did a lecture on this already? You did? Did you? What kind of DAC did you make? Was it an R2 ladder or was it a? Okay. Well, I mean, it's one of those things where maybe we don't have to spend a lot of time on it, but we'll spend a little time with it. How's that? So I thought I would talk a little bit about sort of the basic ideas, and we won't dwell on it. But when I have the difference between analog and digital, first of all, I talk about digitization, its sampling and quantization. I talk about analog values. These are, let's say, a value that can have a fractional representation, like 1.1 volts. And then I like to think in terms of if you have a fixed number of quanta over a voltage range, I should be able to compute what the error is. Let's assume I have an 8-bit analog to digital converter. I know I have 256 levels. I know I got to go from 0 to 5 volts. So now if I take 1 and divide it by 256 and multiply it by 5 volts, that's my smallest voltage quanta that I can measure. That's the error, plus or minus the least significant bit. And so you might say, well, maybe it's 1/2 the least significant bit, maybe it's, within round numbers. So typically when I'm dealing with the outside world, I have a sensor. Right? Let's think about this microphone here. I'm generating energy. It's a pressure wave. It's sound. It impinges upon a transducer in the microphone. The microphone takes the pressure wave in sound and turns it into an electrical waveform. You thought 60 millivolts was small? This is more like 10 millivolts, right? Maybe less. But one of the things about microphones that connect to computers like this is they have what's called phantom power. There's a small 3-volt voltage biased that allows them to power some active components inside of the condenser mic, which give them a little bit of a boost coming out. So you'll be able, if you plug in an 1/8" stereo connector into your audio input, you'll be able to put a voltmeter on it and actually measure voltage coming out of the mic jack. And this happens for camcorders, it happens for computers. These condenser mics are electret microphones, and they require a little voltage on them in order to get some good output. Condenser microphones. A condenser is a very old term. It means capacitor. And so what a condenser microphone is it's a capacitor with a diaphragm, and when the diaphragm is impinged upon with a pressure wave, it changes capacitance. A change in capacitance does not generate a change in voltage. A change in capacitance is something that has to be turned into a change in voltage with some active components. That's why you have to power these microphones. They don't work without it. And they certainly won't do anything to this analog to digital converter without some sort of a mic preamp. So you've got to have an analog amplifier in there. Then comes your digital logic system, which does whatever. I guess that's a computer. And then, although it doesn't have to be, then comes the digital to analog converter, and that's your R2 network, if you like. Or you can build it with a whole bunch of different things. Lots of ways to build DACs. I've built them myself, discrete DACs, and hand sorted the resistors. So we already talked a little bit about voltage ranges. We talked a little bit about sampling. TTL is like 0 to 5 volts, typically nominal. So that's not unreasonable to expect inputs to be properly conditioned for your A to D converter, whatever that may mean. So let's say you're building a biomedical engineering sensor. All right? What you want to do is measure the electromyographic muscle signals that you get when you furrow your brow. You're dealing with millivolts, very small voltages. Some of them will probably be polluted by the ambient electromagnetic interference inside of the air that might include 60-cycle hum and the laser printer with the faulty capacitor and who knows what else. So you're going to have to deal with conditioning the signal. That's a big deal. A lot of analog stuff going on there. A 4-bit DAC. What's that give me? 16 quantization levels. Right? 16 quantization levels, if I have a 1 volt signal going in, means I have 1/16 of a volt of error on my least significant bit. Not very good. There's another way you can put it. You get about 6 decibels of signal to noise ratio per bit. So if I have a 4-bit digital to analog converter, within, rule of thumb, 24 bits of signal to noise ratio. Not very good. If I have a 16-bit MP3 player, or what do they call this? CD. Do people use CDs? Not anymore. I don't know. CDs have 16 bits. That 16 bits will give you something like 96 dB of signal to noise ratio. But there's something else going on when you characterize this. A lot of times they'll tell you it's oversampled. So what happens is they sample that 16-bit CD at something like 44.4 kilohertz. I can hear, or human hearing goes to maximum, let's say 20 kilohertz for round numbers. So what you do is you design a system that can go to 20 kilohertz. With a 44.4 kilohertz system, you start to put a roll-off filter in at about 20 kilohertz, and by the time you get to 22 kilohertz, you've got no energy. The reason you do that is because the Nyquist sampling theorem tells us that you can have harmonics that go up to a maximum of 1/2 of the sampling rate. So if I'm going at 44.4 kilohertz, in theory, I should be able to do 22.2 hertz maximum harmonic content in my input signal. But I can't just have a low-pass filter cut off with a sharp edge. So what I do is I give it a powerful roll-off at the high end, starting at 20 kilohertz and ending at 22.2 kilohertz. So in this way, I'm able to effectively guarantee that the sound levels will be substantially suppressed by the time I reach the Nyquist limit. And that's how CDs work. That's how that's how A/D converters in the CDs work when you do recording, digital recording. They have linear PCM recorders for CDs. So here's the R2 network. What this does is it gives you 2 resistors per bit. It's called a weighting summing amplifier. And what you want to do is you want to get a whole bunch of resistors that are matched, that is, have the same value. If you can do it plus or minus 1%, that's really good. But typically when you go into a parts bin, you'll get maybe 10% resistors. Resistors are usually banded so that you can tell when they're discrete components that you can solder with leads. If they have no band, it's like 20%. If they have silver bands, they're 10%. And if they have gold bands, they're 1%. 1% precision resistors are really exotic, or at least they used to be. Nowadays, with surface mount components, I think you can probably spec the precision of the resistor. So here you go. Here's a ladder where the resistors are going in almost powers of 2. This is a summing network. And so what we're doing here is we're saying, well, we'll start with 1.25 kilo ohms, then 2.5 kilo ohms, which is, double, and then double it again, 5 kilo ohms, and double it again at 10 kilo ohms. And so now we've created a summing junction that we can use with a little feedback op amp, and this effectively will give us the ability to create a 4-bit digital to analog converter with nothing more than, well, let's see, 1, 2, 3, 4, 5, 6 resistors and an op amp. And if you're surface mounting all these resistors, that can be a very inexpensive way to make a very simple output. In fact, if you think about it, you may not need this op amp, right? Suppose you just took all of these outputs, wired them together, and then took the output from that and tapped it. If these outputs that are being output here, if they're all, let's say, relatively high impedance, let's assume this is the output from your Arduino, right? You got, I don't know, digital outputs, perhaps 8 of them. You could get 8 resistors carefully picked, just hook them up, tie them together, and blammo, you've got an 8-bit digital analog converter. So that's a way to go. It's kind of ugly, kind of big, not particularly precise, not hi-fi, and certainly a nuisance if you want to start to go to 16-bit DACs. You need a little bit more resistor stuff. Here's the R2 ladder. With the R2 ladder, you get to use a digital signal to switch the resistor in, and then the resistor divides down the voltage as you put more resistors in a cascaded fashion. And now you don't have to use different resistors. They can all be the same. So now all the R's are the same, and then 2 R's are all going to be the same. And you can find common resistors. This becomes a very inexpensive way to build a DAC. But still, you're better off just sort of buying a component, a digital analog converter component. Not only that, check out how many bits you need coming out of your package. This is occupying 1 bit of your microcontroller's output for every bit on your DAC. So if you need 16 bits coming out of your microcontroller, that's not a good deal. So, and plus, the price of a package is really a function of how many pins it has. So it would be really good if you could find a way to minimize the number of pins in the package. Let's assume you were the DAC designer. How would you reduce the number of pins needed for this package? Right now I see I need 1 pin for voltage reference, 1 pin for ground. I need 4 pins for the digital inputs. I need a pin for the analog output. I need at least 7 pins here. What can I do to reduce the number of pins? Suppose it was a 16-bit DAC. Right? Now I need 16 pins for the data, plus I need voltage input high, I need ground, and I need an output, so that's at least 3 pins, plus the 16, so I need at least 19 pins. This has become a big package, an expensive package with 19 pins. So what do I do? How do I reduce the number of pins? Do what now? Let's assume that the cost of this entire chip is really a function of the number of pins. And if I can go from 19 pins to, let's say, make up a number, 4 pins, 5 pins, I'm much better off. 6 pins. 6 pins would be fine. How can I do it with 6 pins? Any ideas? Well, what if I put a shift register in there and then shift the bits in one at a time using a little clock? Then when it's done, I tell it to stop and start its little settling. I wait for a little bit till all the resistors settle, and then I take a read coming out. Maybe a little, what do we call it, a sample and hold. So in effect, if I put a digital device in here, I can use it as a shift register and then serialize all the bits in. Serially shift them in one at a time. I can have as many bits as I like. In fact, I could even have multiple DACs and choose which DAC I'm using an analog multiplexer. Pick which DAC comes out. So I have a couple ways I can do designs that'll reduce the number of bits, but the basic idea is the same. Trouble is, when I go to buy real-world DACs, we'll find we don't get all of the bits coming out on all the pins, except on the high-end, very expensive DACs. So let's see, we've already talked about the 2R stuff. Let's see some designs, microprocessor compatible designs. Okay. Here's one where, what do we got here? This is the chip. Look at this, 20 pins. Wow. I got digital input 1, 2, 3, 4, 5, 6, 7. Seems like there should be a digital input 0 somewhere. Oh yeah, there it is, least significant bit. So here's 4 bits, 4 least significant bits. Here's 4 bits, the 4 most significant bits. They're all inputs, so they call DI for digital input. Let's see now, what else we got? Plus 5 volts, minus 0 volts, so that's good. I got a thing here called the CS, that's the chip select. I got not write enable. And now what do we do here? We glom it onto the data bus for some microcontroller. We do the chip select. There's some control bus in here, which let's just pick the chip. Let's see, I got a not write enable, so I can take a register. There must be a register in here that latches what comes out of the data bus, and then I can write into that register. I tell it to transfer the data in. I select the chip. Maybe if I deselect it, it goes into a low power state, so I can turn it down or power it down. I get some sort of a op amp to buffer the output and give me a nice current load. And I can use this voltage reference so I can have the voltage coming out range between any two voltages. Plus minus voltage ref. So it probably means I could have it range from 0 to 1 volts instead of 0 to 5 volts if I want to use the external voltage ref. And it might be really good if you had a precision voltage ref. But what some people do is they get a Zener diode, because that's cheap. They figure the voltage will be known, the dropped voltage will be known, and they just pick that off and put in a current limiting resistor. So you can either buy a precision voltage ref, or you can just buy some kind of a Zener diode. Zener diodes will give you like 1.7 volt voltage drops. They're precision. You can fabricate them straight into silicon. Lots of ways you can do this. Because of the noise in the digital system, it wouldn't be good for the voltage ref to be like 100 millivolts, so that you could have this like look like a guitar directly, because you'd be overwhelmed with noise from the switching of the voltages coming out of this microcontroller. Then comes the A to D converter. And the reason you do DACs first is because A to D converters have DACs in them. So A to D converters come in different flavors. There are flash converters, successive approximation converters, slope integration converters, probably more. Let's see if we can't. Digital ramp, that's a slope integration converter. Flash converter. Let's see now. We already know about analog to digital. We already have this basic idea about why we need to sample and how we do quantization. What a successive approximation converter does is it takes a DAC and inputs a voltage that comes from a counter. When the voltage that the counter gets from its register value exceeds the input that you're trying to measure, then you count down. When it's lower than the input you're trying to measure, then you start to count up. So this is what's called a successive approximation A to D converter. And there it is. So the voltage comes in, and it takes the digital to analog converter input, and it compares it using an op amp, also known as a comparator. If the voltage is high, if this voltage is higher than that voltage, then this is outputting a positive 1. If this voltage is lower than that voltage, it outputs a negative 1, or 0. And so then what you do is you use an input clock pulse, and when it's a 1, the clock pulse comes in, and this can then start to count. And what you want to do is you want to have this either count up or count down, in order to be able to successively approximate or chase after the input voltage. That counter's output is the value of the voltage as it has been digitized. So you need a DAC to make an A to D converter. Alright? He's not showing you the up-down part, but this should actually not just be a clock combined with, well, if it was me designing it, I would have the comparator choose whether or not it goes up or down and keep the clock separate. Anding it with the clock. I don't see how that helps anybody. Let's see now. What else do we need to know? Successive approximation AD converter. So let's see. I got the control logic coming in. It goes into the digital analog converter. Goes in through the comparator. Here comes 7.2 volts. I'm either higher than it or lower than it. So what this could mean is I'm walking around it. I go up a little over it, then I go down a little over it. That's called the overshoot and undershoot. Do you need to know when the conversion is finished? If it's in the middle of counting, but you already have latched a value coming out of the counter, no, not particularly. Doesn't matter. You can latch whenever you want to. You can have what's called a free-running successive approximation converter. But most of them say, okay, I'm going to hold the output value steady until you tell me to start the conversion, and then I'll tell you when the conversion is done. Successive approximation converters are better in the sense that they're faster than slope integration converters. Slope integration converters, what they're doing is they're sampling into a capacitor for a fixed amount of time, and that gives them the ability to do an ADD conversion. Let's see now, what do we got? Flash converters. These are the fastest. Also most expensive converters. When I was in school, the flash converters were able to do CMOS silicon on sapphire fabrication that could run faster than video rates, which was considered quite fast at the time. And then that way you could digitize composite video signals and build things like frame stores. And what you need is a separate comparator for each bit. That's kind of a nuisance, really, because the comparators are analog and they take up a lot of space. 16 op amps is kind of a lot if you want to build a flash ADD converter, but it's doing the conversion in parallel. So in some sense, I guess you could make the claim that it's inherently faster. You don't really have to wait for conversions to be guaranteed to be done, because the encoder will always give you a nice digital output. Probably want to latch it anyway. And you'd probably want some kind of logic to select it so that it can assert its output to the bus. Because normally a digital bus is going to be shared with other components. Similar to the question that I had before, how would you, was that me beeping? Was that your beeping? Okay. Similar to the question before, how would you reduce the number of pins? I would say you could still use a digital circuit. Take the output, run it into a shift register. Oh, this is a 3-bit ADD converter. How many comparators do we have? 1, 2, 3, 4, 5, 6, 7. So 2 to the 3 is 8. So an 8-bit converter needs 256 comparators. That's a nuisance. A 10-bit flash converter would need 1,023 comparators. Yeah, that sounds pretty inelegant to me. Let's see now. Propagation delay through the network means propagation through all of these resistors and then through one of the comparators. So how fast does a comparator run? Fast. You can get them really fast, and you're only going to have to worry about one comparator delay plus resistor propagation time. Let's see what else we got here. Analog devices makes a whole line of wonderful D to A converters and A to D converters, but a lot of companies do. And here's an interface with parallel outputs, 8 bits for the A to D converter. It looks like he's got a chip select, a not read, not write, an interrupt that can come out of the chip so that it can indicate to the processor when conversion is done. So what this says is I can tell it to start and then get an interrupt back when the conversion is complete. Let's see what else we got here. The converter. The A to D converter's got its own clock, right? Because it's got a counter, and the counter is running at its own rate. And so when the A to D converter is spec'd out, you can either use the counter inside the A to D converter, or you could have an external counter, perhaps a timer, part of your microprocessor, powering the A to D converter. Let's see what else we got here. Here's your transducer. It looks like a potentiometer, right? Potentiometer is characterized by having a wiper, and what it's doing is it's creating a voltage divider that goes between 0 and VCC volts. Probably that's not real good, because if the voltage coming in is 0, I guess it's not going to take any. Oh, I see. It's using V in. So that's the smallest amount, and here's the V in coming in. So presumably it's digitizing the wiper position. So you could use this as a digital control. Now let's see what's going on. This here is tri-state output latches. Tri-state, normally in Boolean algebra you think everything is 0 or 1. But there's a third state. The third state is the high impedance state. You need a high impedance state for circuits that are going to be hooked to a digital bus because... Why? Why do I need the third state? If you have outputs and you hook them to outputs, let's say you take two AND gates and you hook them together. Their outputs are hooked together. What will happen? Think about voltage, right? One is asserting a 1 and the other is asserting a 0. A 1 is equivalent to 5 volts. A 0 is asserted to ground. What happens when you take 5 volts and you hook it to ground? Well, you're not allowed to sit like lumps on bumps. You should be able to tell me it's a short circuit. You can't just hook 5 volts to ground with no resistance in the way, no load, because that's like taking two poles of a battery and hooking them together. It makes the wire hot and the battery dead. So what you want to do, and oh, by the way, if you did do this, the transistors inside of the NAND gates would try and sink as much current as they possibly could until they blew out. So you'd blow out your NAND gates. You know, you'd be blowing out the circuit. So a tri-state system essentially says I've got outputs hooked to outputs, but no two outputs will be asserted at the same time. So when the chip, this A to D converter, is hooked to a microcontroller's bus, it will not assert the bus data at the same time as some other peripheral, like the RAM. Because that wouldn't be good, because that's outputs hooked to outputs, zeros hooked to ones. And you'd have 5 volts hooked to ground, and everything would blow up. Or blow out. It's not substantial current, but it's enough to like make it get all hot and unhappy before it blows out. So you need to use your chip select and make sure only one chip is selected at one time. Otherwise what happens is when you wire all these things to the same bus, you've got a problem. And that problem is you've blown out computer components. So that's not good. You have, if you have a bus where you're plugging in cards, you want to make sure that each card is selected only one at a time. Right? Because the buses are all wire-ored together. And you don't want data to be asserted 0 against 1. Does that kind of make sense to people? Hope so. 'Cause that'd be bad. So some of these things you can recognize. That looks like an SR latch to me. This looks like another SR latch. Let's see what else we got here. Here's a successive approximation register latch. Now that's going to be an 8-bit sample and hold coming off of this shift register. Now let's see what this is doing. I got a flip-flop in here which is looking like a clock. Here's my ladder decoder. That's my DAC, my R2 ladder. It goes to my comparator. So here comes my input voltage. The comparator runs up against the input voltage, and it gives me an up-down count off of the my SAR latch. Let's see what else I got here. I'm not really seeing this as a clock. Why is he calling it a latch? I guess because he's using the shift register. So he takes what comes out of the shift register, he runs that through a latch. Looks like he's building some kind of an ad hoc counter with this flip-flop, and then cycling it back into the shift register to count up or count down. That's very hacky. That's a very hacky way to build it. Me, personally, I would have just said, okay, let's get a counter, run it up or down depending on the comparator output, and then run that into the digital analog converter. What else do we got here? Here's a transfer, an internal thing called transfer. And it looks like he's got this being hooked to the SR flip-flop, which goes into an interrupt to indicate when things are done. Input protection. Oh, here's his little external oscillator. I guess this is an internal oscillator. He says clock oscillator CLKS. I'm not sure where that goes. I don't see it here. I see clock B, I see clock A, I don't see CLKS. That's a fairly unsatisfying diagram in my view. What do we got here? This one looks like it says multiple A to D converters with the Z80. I think we can safely skip that as being too complicated for now. So now what I'd like to do is take a break and then get back to hot in here. Maybe we should try and open a window or something. I know, it's really terrible. Let's do that. We'll take a break, and I'm going to go out to the hall and